Welcome to linear algebra. Have you ever looked at a massive, messy system of equations and wished there was a magical machine that could just spit out the answers? Well, that is exactly what we are going to learn today. We will explore the reduced row echelon form, which is the ultimate, most organized state a matrix can possibly be in. By the end of this lesson, you will understand how to transform any chaotic grid of numbers into a clean, simple solution. Before we dive into the math, let us understand why this concept matters. Imagine you have a very complicated recipe with confusing prices for apples and bananas. You just want to know the simple price of one apple. In linear algebra, we use grids of numbers called matrices to represent these messy systems of equations. When a matrix is messy, the solutions are hidden. Reduced row echelon form is like an organizing machine. It cleans up the matrix until the answers are staring right at you. To do this, we look at rows, which are horizontal lines of numbers, and the leading entry, which is simply the very first number in a row that is not a zero. Now that we understand what a matrix is, let us look at how it reaches this perfect state. For a matrix to be in reduced row echelon form, it must pass 4 strict tests. First, if there are any rows made entirely of zeros, they must be banished to the very bottom of the grid. Second, the leading entry in any non-zero row cannot be just any number. It must be exactly the number 1. Third, as you move down the rows, each leading one must be further to the right than the one above it, creating a downward staircase pattern. Finally, and most importantly, each leading one demands absolute zero everywhere above it and everywhere below it in its vertical column. These 4 rules we just saw lead us to a specific mathematical structure. Here is what a generic matrix looks like when it has successfully reached reduced row echelon form. Conceptually, this represents a fully solved system of equations. Let us break down the symbols. The number 1 represents the leading entries. Notice how they form a perfect diagonal staircase moving down and to the right. The number 0 represents the cleared out spaces, showing that every column with a leading 1 has zeros everywhere else. Finally, the symbols A, B, and C represent whatever numbers are left over in the final column. If this matrix represented variables x, y, and z, this highly organized grid simply translates to x equals a, y equals b, and z equals c. If those final numbers change, your solution changes directly with them. Before we move on, let us see this with a concrete example. We are given a simple system of 2 equations. X plus 2y equals 5 and 2x plus 3y equals 8. We are asked to convert this into reduced row echelon form. We start by writing the numbers into a grid with 2 rows and 3 columns. Our top left entry is already a 1, which is perfect for starting our staircase. However, we need to eliminate the 2 sitting directly below it to start forming our columns of zeros. To do this, we replace the second row with a new row, calculated by taking the second row and subtracting twice the first row. This arithmetic forces a 0 into that bottom left position, giving us a new second row of 0, -1, and -2. Continuing with our matrix, we look at the new second row. The first non-zero number here is a -1, but our strict rules state that every leading entry must be exactly +1. To fix this, we simply multiply the entire second row by -1. This flips the signs, giving us our required leading 1 and changes the -2 into a +2. At this stage, the matrix is in a basic echelon form, but it is not yet fully reduced. The leading 1 in the second row has a 2 sitting directly above it. To achieve the final reduced form, we must turn that 2 into a 0 by subtracting twice the second row from the first row. This crucial step clears out the space above the second leading 1. Now that we have performed our final row operation, let us look at the result. The matrix is now perfectly in reduced row echelon form. We have our downward staircase of ones and zeros everywhere else in those columns. We can now translate this highly organized grid back into our original equations. The first column represents x and the second represents y. The top row now simply reads x equals 1 and the bottom row reads y equals 2. We have successfully solved the system by organizing the numbers into their simplest possible state. The physical meaning here is that the two original lines intersect exactly at the point 1, 2. Having solved a simple system, let us see what happens when a system does not have just one single answer. We are given a slightly larger matrix with 3 rows and 4 columns. Our goal remains exactly the same: to create a downward staircase of ones with zeros everywhere else in their columns. Our first goal is to clear out the numbers below the top left one. We see a 2 in the second row, so we will subtract twice the first row from the second row. When we perform this subtraction, something interesting happens. Every single number in the second row cancels out perfectly. The entire second row becomes a row of zeros. Continuing with our larger matrix, we now have an entire second row made of nothing but zeros. According to the strict rules of this format, any row made completely of zeros must be banished to the very bottom of the grid. Therefore, we swap the positions of the second row and the third row. This restores our downward staircase pattern. Now, we have a leading 1 in the second row, but the number directly above it is a 2. This violates the rule that a leading 1 must be the only non-zero number in its column. We subtract twice the second row from the first row to eliminate this 2. This final cleanup step brings the matrix into its ultimate reduced state. With our final cleanup complete, let us analyze the result. This final matrix perfectly satisfies all the rules of reduced row echelon form. Notice the beautiful downward staircase pattern of the leading ones and observe that every column containing a leading one has absolute zeros everywhere else. However, look closely at the second column. It does not contain a leading one. In linear algebra, this tells us that the second variable is a free variable. Because it is free to be any number, the physical interpretation is that the system of equations has infinitely many possible solutions, all of which can be easily read from this final grid. Now that we have calculated these matrices by hand, let us look at a visual representation of what we are actually building. In this diagram, you are seeing the perfect structure of a reduced row echelon form matrix. The bright blue numbers show the required staircase of ones moving diagonally down and to the right. The bright red numbers emphasize the strict requirement for zeros above and below those ones. The black letters A, B, and C represent the final solutions. This visual pattern is exactly what computers look for when solving massive systems of equations. It is a perfectly clean, standardized grid where the answers are immediately obvious. This visual pattern we just saw leads us to an important question. Why does this matter in the real world? When engineers design massive suspension bridges, they create systems of thousands of equations. These equations ensure the physical forces balance out to zero, so the bridge does not collapse. Solving these by hand is completely impossible. Instead, computers use algorithms to convert these massive chaotic matrices into reduced row echelon form. Once the matrix is in this highly organized state, the computer can instantly read the exact tension required in every single steel cable. Without this standardized, ultimate simplified form, software would not have a reliable way to extract answers from complex data. We have covered a lot of ground today, so let us reinforce the most important ideas. First, reduced row echelon form is the cleanest, most simplified version of a matrix. Second, remember the strict rules. All zero rows must be at the bottom, leading ones must form a downward staircase, and there must be zeros everywhere else in the columns containing those leading ones. Finally, reaching this form guarantees you have found the simplest possible version of your linear system. You now have the ultimate tool for revealing the exact solutions hidden inside any messy grid of numbers. Great job! You have covered the full topic.